or sometimes people call it validation. What we do now, what we do here is concept repair, but we have to validate. Is this good or bad? Is it acceptable or not? Do we need additional thickness for the doubler? So what we do, there's many checks to be done. For this, that's not to confuse. What we need to do, we need to see there is margin. This is margin. Okay, sorry. So there is factor of safety, which is in aircraft by regulation 1.5. We have to meet that requirement. So the ratio S ability on the doubler with the original normally should be 1.5, depending on type of the structure. If the structure secondary, not primary structure, maybe we enough with looking at the margin of safety, which is positive. However, for the primary structure, for the critical structure member, you need to show, you need to validate the doubler strength over the original material strength has to be as minimum as 1.5. What does it mean? It means if the original carry 100, original able to carry 100 meters. For you to get the 1.5, you need to design the doubler of 150. Because factor safety equal design over applied, and we got 1.5. It's how we try to understand the factor safety. Means what? Means we have this 50. Okay. This doubler having 50 Newton extra. We have extra. Whatever happen, we have extra 50 Newton. We're not gonna load the structure to 100, more than 100. You limit to 100 only, because that's required to get 1.5. So we always have 50 Newton extra. What is this 50 Newton extra? For errors. If we make errors in design, errors in manufacturing, maybe you cut a bit short, maybe your material is a bit thinner. Error, okay, and also environment. Maybe we have corrosion. Environmental effect. You may have corrosion build-up. So you'll be able, still be able to have a safe structure until someone saw there's defect and repair. So that is what we need this extra. Okay. Questions?
I think no, sir.
No, huh? Okay. Next is we have to do the how you gonna check the validity or the strength of the doubler? So we have, whatever you do, you have to go back to the fundamental. Stress equal force over area. Okay. Force or load will be equal stress time area. So what are you looking for here? You are looking for load loss. Remember earlier I've been talking about you remove the flange. Okay. You remove the horizontal flange, you have lost the load ability, the load carrying capability. So load loss due to removal of the flange, horizontal flange. So how you want to calculate that? You have to use this equation again. So the load loss, which is force, sometimes we put P, sometimes we put it FP, but just say load loss equal to stress time area. Area is what? Area is cross-sectional area. Here is the cross-sectional area of the angle. So what is the stress? Stress is what you get from the, remember I've been talking about stress and strain. So as we pull the structure, we test them and we come to the point where it breaks. So this one is maximum stress, FTU. Before it break, it has start to yield, start to give away. So here is FTY. Sorry, FTY yield. So if yield after the yield point, okay, this region we call it elastic. So yield we call it plastic. This is plastic. Once you reach this plastic region, you have potential of deformation. If you release the load, it will not come back to original point. This is permanent deformation, which is not acceptable in aircraft structure design. So that's why we have to check either, okay, you have to check FTY time 1.5. Okay, that's why if you look at the SRM, you have to verify either you select FTU, which is here, okay, which is here is 390, or 1.5 times FTY. So FTY here is 230. If when you multiply FTY with 1.5, you get 345. 345 is somewhere here. Say here is 345. 345. So now we have to choose the minima, FTU or FTU okay, FTU or 1.5 times FTY, which is minima. What does it mean here? After you multiply 1.5 to the FTY, 1.5 multiplied to the FTY, you will get 345, which is somewhere here. So the FTU is far higher, 390. Mean that the material has gone to very far into the plastic region before it breaks. Mean that if you come to this point near the break, it will be deformed. We don't accept that. That's why we use the critical 345. 345 obviously is higher than FTY, it's already deformed. However, not as much as the FTU, before the FTU. So we choose 1.5 times FTY in the analysis. So always do that, always check that. Questions? Okay, now we have problem. How do we get this value? So to get this value, you go to 51. You can see here is 51, 17, 11, table 2. So you go to 51, 70, 11, table 2. 3, table 4, table 2. Okay. Okay, let's look at table 2. Let's explore table 2. Table 2, how we want to see the table 2? Okay, you can see table 2 here, 2024 T42. Yes, it's table 2. Sheet or clad sheet? I think we have stated earlier is clad sheet. So clad sheet, you go to this clad sheet, this is here. Okay. Now T42, this is T42 clad sheet. And then you look at value here. FTU, FTY. So you always zoom into this. Okay, the 390. And then you look at the FTY. So I will zoom further here. Okay, let's look at a bit more. Zoom it further. Okay, further. Okay, see here, two things you need to see is A value, A value, B value. Another thing is L, LT. I think I have explained to you earlier. This is L and here is LT. You have to choose either A, B, L or LT. Okay, let's look at A first. A, basis value used in the LT material direction. Okay. L, A and B. Okay. A is the value when they did the test. Most of the time they got this value 395, 390. Okay. The most value they get. But they'll get sometimes they got 405, 400. So mean this 395 and 390 value is more accurate because during the test they get this value percentage of them during the test they get the strength for L 395 390 for LT more than they get 405 and 400. This is megapascal. Okay. Why this is important? Because A is more conservative, B is less conservative. When they use A for the primary critical structure. So they use A. Why? Because A tends to have lighter structure. Okay. So you have you be more conservative. Then what is L and LT? L and LT is the roll. When you do when they make the material for the plate, okay, they come into a roll. Okay, roll. So as they spread the roll, they say to you, so the direction the roll is L, the direction perpendicular to the L, the roll is LT. Why is important? Because the grain of the material will be according to the L. So if you pull the load, so this is stronger. But if you pull along the LT, this is less stronger because will easily break the grain. So that's why you can see value here is 390 and then the L is 395. You can see the differences 5 megapascal between L and LT. To be conservative, we use A and LT. Okay, A and LT. Okay. That's why you can see the value that we chose is 390 ALT and 230 for the FTY A and LT. You can see here value here 390 230 and composite here is 235. This one we use to this value is for you to check failure of the doubler and FCY here to check the failure of the bearing. Okay, this is for the bearing FBRY. And here is to check the shear failure of the plate. Okay, what can happen? For any splice, what can happen? You may fail in various ways. So just put a simple splice. Simple splice, we have here a plate and put another plate. Just put an example earlier. We have another plate coming out here. We have two fastener here. Okay. This is the plate we pull. Maybe you just take a section of this. So imagine. So we can see from the bottom, we put a two rivets. So what can fail? We may fail the plate can be cut off through here. They call this as net tension failure. And the fastener may migrate through here. That's why we have to have good edge distance. The fastener may came out through here. Okay. That's why we need to have a good edge distance. So we call here as shear out. Because it's the fastener will be shearing off to the edge distance. This is net tension failure. Okay. So for the net tension failure, we use the 345. For the shear out, we use 220. And then you may have bearing failure. So bearing means the hole here may be elongate. Okay, make a oval. Then to determine the bearing failure, you use the FBRU. Formula are the same. Net tension failure is still stress, the force. The force for net tension failure will be force stress, okay, time area. Or you want to look for the stress, force over area. Similarly here, shear out is still use the same formula. Force equal to stress time area. Or stress equal to the load on the plate over area. And this stress will be compared with the material strength.